Okay, everybody got one? Thanks. Okay, would you fill in that top thing without looking at your other paper? That little starter question there? One squared variable? Parabola. Got to be a parabola. Okay? Two squared variables for the rest of them. Same sign and same coefficient. That's going to be a circle. You studied that in 2.4. Okay? Same sign, different coefficients? That's going to be an ellipse. And then the only thing you need to check for a hyperbola is that they have different signs on those squared variables. So that's going to be a hyperbola. Okay, and again, you have to have the variables on the same side in order to use those rules. Okay, so just like for a parabola and a circle, ellipses come from a definition. Now, I went through and showed you exactly where the formula comes from, that nice graph-friendly form, the x minus h quantity squared 4a and then y minus k. I showed you where that comes from. We could do the same thing for ellipses and the same thing for hyperbolas. All right, I'm not going to derive each one of those. Instead, on this one, I'm going to show you an animation that shows you how ellipses are formed from the definition. Okay, so here's the definition. An ellipse is the set of points on a plane, the sum of whose distances from two fixed points. So there's that fixed point again. Last time when we were doing parabolas, the fixed point was a focus. We only had one. Now we've got two. Okay, so the sum of the distances is constant. So if we add up the distance between these 2 points and a point on our ellipse, it's always the same. Those two fixed points are called foci. You could call them foci if you want. Most people say foci. I think that's the proper pronunciation. Or pronunciation if you like. Okay. And a lot of times I'll bring in a string and we'll have two foci on the board and we'll kind of draw an ellipse. But I'm going to show you an animation. So I want you to take a look at this. Let's see, where are we? Take a look at that right there. I'm going to flip the light off so you can see the colors a little bit better. Okay. Look at the lines up at the top. So this is the total length. You'll notice the total length never changes. It's always 10. But that total length is made up of a blue part and a red part. And as the blue part gets big, the red part gets small, and vice versa. That red length represents the distance from this point, this focus, to a point on the curve. And the blue line represents the distance from the same point, but over to this other focus. If we add up, so think of this as a string. The string is always exactly the same length, but as you stretch it, as long as these 2 points are different points, we're going to end up with not a circle like you normally get. If you have one fixed point and then a constant distance, we ended up with a circle. Here we end up with an ellipse. So what would happen if we took these 2 points and slid them really close together? It would look a lot like a circle. What if we spread them really far apart? Okay, then we get something that's not quite as tall and really wide. Okay, we get a really squished ellipse. Okay? Does everybody see how those relate? It's the set of points, the sum of the distances between a point on the curve and these two fixed points, these two foci, is always the same. In this case, it was 10 just for this demonstration, but we could make it lots of different things. Okay. Good? Okay. So let's go back here and let's again describe what's going on. Okay, from those previous sections, we know that if we've got an ellipse, we've got to have two squared variables that have the same sign and the same coefficient, but different coefficients. Oh, did I? Different coefficients, thanks. I should tune in. Okay? And they are very similar to circles. In fact, toward the end, tomorrow, I'll show you how similar they are. But just like a circle, if we're going to put them in a graph-friendly form so that we can easily plot them on a plane, you've got to have two perfect squares in them. So this is a nice, easy circle to graph. This was a nice, easy parabola to graph, perfect square. If we're going to graph an ellipse, we've got to have a couple perfect squares. And then we've got some important features that we're going to have to graph. And as we get more complicated, there are more features. With a parabola, we just had one focus, one directrix, a vertex, and then the endpoints of the lattice rectum were all set to go. With an ellipse, we've got a center, we've got two foci, we've got two vertices, and then we've got a major axis and a minor axis. And those are the things that we're going to want to graph and label when we do an ellipse. Okay? So we're going to take a look at this one right here. It's already in a nice graph-friendly form, and I'm going to show you how to graph this one. So if we have an equation that looks like this, you'll notice that they're both positive, and because A and B are different, if you slid that out front and thought of it as a fraction, they have different coefficients. Okay, this has a center at 0, 0. Got to pay close attention. From the center, we go A units in the x direction. Here's why. Find the variable you want, in this case x. Underneath it is an a squared. Take the square root of that. That's how far you go in that direction. Okay? If we looked underneath the y, it's got a b. So we're going to go the square root of that in each direction. So that would just be b in each direction. The major axis is determined by whichever is bigger out of A or B, A and B. The focus are always located on the major axis. The major axis is always the longer axis. The minor axis is the shorter one. Okay? And remember, I said this before. I don't kind of restate it here. The foci are always inside the curved part of the conic section. So they're always going to be inside the ellipse. They're never going to be outside the ellipse. Okay? And the foci are C units from the center on the major axis. I'm going to go to right there, and then I'm going to talk about how we can find what C is. So if we were going to graph this, here's what we'd graph. The center is at 0, 0. Underneath the x is a 25. Take the square root of 25, you get 5. So we're going to go in the x direction, the square root of this number. So I'm going to go 5 units in this direction and 5 units in this direction. Then I look at the other one. Underneath the perfect square with y is a 9. Take the square root of that number and go that far in that variable's direction. So the square root is 3. We're going to go 3 units in the y direction. So that means 3 units up and 3 units down. Okay, now it can sometimes be difficult to draw these, so sometimes what I'll do, you don't have to do this, but this can be helpful, especially in the long run. Sometimes I like to put a little box around this, and then I say, okay, my ellipse looks something like this. These lines can kind of help you draw an accurate ellipse. Okay, mine looks like a cross between a potato, a football, and an egg, but there we go. Okay? Okay, this right here is the major axis. This right here is the minor axis. Major's the big one, minor's the small one. Okay, we've graphed a couple of these things. Okay, let me do the vertices. These endpoints right here, the endpoints of the major axis, that's a vertex, and that's a vertex. And now we want to graph the foci. We know what the center is, but we want to graph the foci. The foci are C units from the center on the major axis. C units from the center on the major axis. Now, how do we figure out what C is? Okay, we use this little formula right here. It looks a lot like what? Looks a lot like the Pythagorean theorem. Here's why they're not added together. If you added the square of this plus the square of that and then took the square root, it would be bigger. It would be outside either one of these. It would be bigger than 5 and it would be bigger than 3. We don't want it outside. We want it inside. So we're going to take, this is the big one squared minus the little one squared. This, I think, is a better way to think of it. That equals C squared. Okay? Now, if you think of it that way, it's always going to be A squared minus B squared, big one squared minus little one squared. I'd really prefer you think of it as the big one squared minus the little one rather than this, because then you don't get screwed up. Okay? And it's also easier to understand why the formula is going to be a little bit different when we do hyperbolas next week. Yeah?
Why is A squared always the big one?
Because it's the major axis. I don't really care whether you call it A or B. I just want you to do the big one minus the little one. Big one squared minus little one squared. Okay? You can get hung up on a detail like that, and I wouldn't bother. Okay? It also screws you up when you start doing hyperbolas. Okay? So don't worry about which one's A or B. It doesn't really matter. Okay? Think of it as big one squared minus little one squared. To be mathematically precise, they have to write stuff like that so you can write down a formula. You're never going to see anybody write in a textbook, hey, do the big one squared minus the little one squared. But that's the net effect of what you need to do. Yeah?
So if the ellipse was squished so the y-axis was taller, would we switch A and B?
If you wanted to think of that, but then the one underneath the y would be bigger. So just do the big one squared minus the little one squared. If you got technical, you'd have to call the one underneath the y the A because it's the bigger one. Okay. Again, a detail you can get hung up on. Just think it's always going to be the big one squared minus the little one squared. And why is it minus? Because you've got to make sure it's inside that little rectangle that we drew, that little ellipse that we drew. With me there? So in this case, if I do the big one squared minus the little one squared, that would be 25 minus 9, right? And that would be C squared. So what's C? C is 4. C is 4. So that means I'm going to go 4 units along the major axis this direction and 4 units along the major axis this direction. And there are the foci. Any questions? Okay, watch please, because I find this to be a little bit better as far as labeling. You could try and squish everything on the inside right next to where it needs to be. Or you could do this. Let's do a vertex down here. Okay, so we're going to label it down here. We're going to do a focus there. We'll do the center here, focus, and vertex. The center was 0, 0. How far did we go either direction, left or right, to get to the focus? 4. So this is going to be 4, 0, and that's going to be negative 4, 0. And how far did we go along that major axis in the x direction to get to the vertex? 5, 0, and 5, 0. Okay, a lot of times that's easier than trying to stuff everything inside. And if you wanted to do vertex, focus, center, focus, vertex, that'd be great. Okay, any questions? Okay.
Yeah, why don't you label the other ones?
What other ones? These guys up here? They, this textbook doesn't consider those vertices or anything. I think they're important. We should probably, I mean, we can label them. They're not vertices or anything. But this would be 0, 3, and this would be 0, negative 3. Okay? Oh, negative 5. Thanks. Okay? Anything else?
Yeah, what do you do with the one out front? Did you explain that already?
Oh, this one right here?
Yeah.
You don't need to do anything with it. That just comes from it being in a graph-friendly form.
Is that always a one?
It is always a 1. It has to be a 1. Yes. Yeah, until all of us are gone. Yes. It will never not be a 1.
It's just like you can't buy.
Let's say it was a 7, and I said you've got to make it a 1. It's an equation, right? How could you turn a 7 into a 1? Divide both sides by 7. If that turned out to be a 7, just divide both sides by 7. You'd have a factor of 7 down here and a factor of 7 down there. They'd be ugly numbers, but can you still make that a 1? Okay. All right. Again, just to emphasize, in this formula, it's always going to be the big one squared minus the little one squared. So if you're looking in the textbook or looking at anything else, a squared is always the big one. A squared's always going to be the big one. Okay? Now, don't get too hung up on the details or anything, but it's always just going to be the big one squared minus the little one squared. Okay, any questions there? Okay, let's take a look at the next one. Let's just go ahead and graph this. Where do you think the vertex is? Center, thank you. Where's the center? Okay, so it's going to be opposite of this. That's going to be 1, and then -1. So 1, -1, so we're right here. That's the center. What variable is this right here? X. What's underneath it? A 9. So we're going to take the square root of that. That's going to be 3. So how far are you going to go in the X direction? 3. So we're going to go 1, 2, 3 over here. 1, 2, 3 over here. Three from the center. Okay, look at this variable right here. It's a y. Look underneath it. It's a 25. Take the square root. We get 5. How far do we go in each y direction? 5 units. So we're going to go up 5, and we're going to go down 5. What's different about this one? Yep, same shape, it's just been rotated 90 degrees. It's got a vertical major axis rather than a horizontal major axis. So if I draw what this one looks like that. Okay. What are these points right here called on the ends? Those are vertices. Okay, so let's label the vertex, let's label the center, and let's label that vertex. If this is 1, -1, then this would be 1, 4, because we went up 5, right? Up 5 from -1. This would be 1, -6. Okay, if I wanted to label these points right here, that would be fine, as long as you plotted them correctly. I think we're in good shape. Wouldn't be a bad idea to do that. That's going to be -2, -1, and that one right there is going to be 4, -1. Okay. Again, you could get hung up on, hey, wait a minute, which one's a squared and which one's b squared? Or you could just remember, it's always going to be big one squared minus little one squared. Same thing, right? We end up with 4, so I'm going to go 4 units up here. That's going to put me right here, and 4 units down here. So I can then label the foci. So on this one, notice what these all have in common. They have all the same x coordinate. If I went up 4 from -1, this is going to be 3. And if I went down 4 from -1, this is going to be -5. Any questions? Okay. This is pretty much filled in for us. The center would be at h, k. But in this case, that's going to be 1, -1. Again, we looked underneath the x squared term, look underneath the y squared term. Major axis is longer, so it runs vertical. Okay, how long is the major axis? 10 altogether. How long is the minor axis? It would be 6 altogether. Foci are c units from the center on the major axis, and do big 1 squared minus little 1 squared equals c squared, and that's where we end up. Okay, any questions? Okay, here's what I want you to do. Parabolas are due tomorrow at the beginning of class. Be done with 7.2, and you need to at least look at a couple of the problems in 7.3, okay? Then you'll get the weekend to get that one done. Have a great day. Somebody flip the light.